Stay with me, phone. There you go. Whoa. All right, so this is 35. The one about the minute hand of a clock?
Yeah.
Yeah.
What section?
It's 3-9. So the minute hand of a clock, if it has length R, where'd you go there? Find the rate at which it sweeps out area as a function of R. R. Now, for example, so it's going to move through some angle, and then want to know how much area it's swept out. The rate at which it's sweeping that area out. The first good thing to think about is, what is the area of that thing that just drew? Remember, it's the area of a sector of a circle. It's almost too nice to believe this thing. You guys remember this? Like, so you draw like this just so it's easier to look at. This S equals something or other. Oh, wait, R theta. Okay, R theta. I'm with you. Sorry, I thought you said degree something or other. R theta. So you're right. Radius times theta. Does that sound familiar? A little bit. All right. Now, what is really, really cool? You actually can prove this, and the reason this works is because if I zoom in, if I made theta smaller and smaller, wouldn't this edge get more and more linear? It's the whole idea of zooming in, and it looks more and more linear the more I zoom in. So this is amazing to see. You can prove this in other ways, but basically the area of this sector is the area of the triangle, assuming that this is flat. It's kind of neat. So the area of a triangle is 1/2 base. Well, the base would be R theta times the height, and the height would be the radius. So it's 1/2 R squared theta. Hopefully that sounds vaguely familiar. The pre-calc stuff.
Instead of pi, you deal with theta.
Well, I mean, pi is a specific angle.
Specifically.
Way too specific. I want the general area of any sector, not half the circle. Is that cool? Yeah. Okay. Where am I at? Oh. So if I look at a specific situation, the area of a whole circle would be pi r square. So the area of half the circle would be 1/2 pi r square, right? And that's the angle would be pi over 2. So it's if I went the whole circle around, what angle is that through? 2 pi, and the area would be 1/2 that. I mean, that's kind of like a specific situation where I let the theta be a specific angle. So you kind of recover things that we know have to be true, like pi r squared. All right. So this is just knowledge going in to this problem, right? So then it's asking you find the rate that it sweeps out area, so dA dt. Yeah, so now that you got the function that you're dealing with, not too hard. What's the relationship between, they tell you, where'd he go? Yeah, all right. Oh, one little thing there, let's see. Oh, all right. That's too funny. What's if you take the derivative of this, what's going to happen here? What's happening as this is moving? As this is moving, the area is increasing that it's sweeping through, and the angle is also increasing, right? So both of these are functions of time. You with me? All right, so there's a little extra layer on top of this that I want you guys to think about. If you try to take this guy's derivative, what happens? What do you have to figure out on top of this? Yeah. Of course, one of those things we know. How long does it take the minute hand to go all the way around? 60 seconds, right? So therefore, you could break it down to what must d theta dt be. You can figure out. Yeah, how many radians does it go through in how much time? How many radians does it go through? 2 pi. In how much time? 60 seconds. All right. I've given you enough to think about to try to do that problem. Okay, I like it because I can see in your eyes a lot of you haven't tried this one yet, so I don't want to say anything until more try it. But I've given you a lot to work with. Okay. First thing was just remembering what the shit this was. Okay. Anything else from homework stuff?
I have a question regarding like the section. So I've noticed that there's quite a few like different area formulas that we need to know. Is there like anywhere that in the book that we can see all of what we need to know?
Yeah, I mean, there's a bunch of them back, like I said last time, on the first page of the reference card, in the back, yeah.
Okay.
The first thing you do, well, 2 things you do when you get a new math book. What kind of answers do they tell me? I don't blame you. Same thing I did when I was a student. And also, what the hell's in the front and the back? What kind of reference material is already there? So I don't have to like go searching somewhere else. Yeah. But you always got Google. You always got whatever past books you held on to. The further you get in math, the more you realize you want to keep those books. You don't want to just get the money back for them. You hate yourself. I still got my calculus book from way back. Good on you, Jeff. Yes?
I have another question regarding textbooks. Would you recommend investing in the bigger Stewart calc books?
Well, there's a book that only does Calc 1 and 2.
Yeah.
And then there's the big ass book that's got all 3.
Yeah.
So if you got to go through 281, then might as well, right?
Well, isn't the 8th edition in that series of books the newest one?
Yeah. The possible problem you run into is by the time you make it to Calc 3, maybe we've changed editions. Yeah.
Exactly.
And we're actually trying to go towards open. I am definitely in my classes going towards open source books. Like, but courses like 110 and 180, 280, I don't want to necessarily do that because if somebody takes my 180 and then takes somebody else's 280, and I have an open source book and 280 says, "Oh, you've already got the book," and they're like, "No, I don't." With this shit, so it'd have to be a departmental decision to switch over. So why am I saying all that? Because eventually we're going to switch over to open source books. Thank God. I'm so sick of dealing with publishers.
So what do you mean by
If any of you are watching this.
Just like an online book or what?
Yeah, like in my stats class, there's an open source book, meaning they can go online, download the PDF.
Yeah.
They could pay like $35 through Amazon to get a hard copy if they want. $35 for a textbook. What the shit? It's about 1/6 the normal cost. So it's either free if you do the PDF, or it's $35 or whatever if you want a hard copy. So that's where we're trying to move. And those books are all written by math teachers that aren't looking for a lot of money. They just want good, cheap stuff for the students, which only makes sense. Get the publish out of here. Go get a different job. Stop buying our shit with all these bells and whistles. Only $190. Get away from me. I don't like that. Sorry. I'm in a ranty mood today, so I'm going to try to do what I can to bring it back. Okay. You guys are like, I don't care about this shit, Jeff. I'm sorry. Is that all right?
Yeah.
Okay. Anything else? Yes.
20 on 0.7.
Ooh, Newton's law of gravity. Blah, 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 blah. Oh, cool. I like this. So which part did you have some trouble on?
I don't remember.
So the first part is just find DFDR. That shouldn't be. So this is all about Newton's law of gravity, right? That one? I mean, look at the right one. Yes, 3.7.
Yes.
Number 20.
Yes.
Newton's law of gravitation, right? Okay. So that's the force of gravitational pull between two masses. Which symbols do they use? Okay, little m, big M. Yeah, there's going to be a gravitational constant, and then it's going to depend on the square of the distance between the two. This idea of the inverse square law, like if you have something putting sound out, the intensity of the sound decreases as the 1 over the radius squared because it's kind of like coating the inside of a sphere around it. Same thing with light. The intensity drops off as 1 over r squared. So you see this idea of an inverse square law in a lot of different physical phenomena. Here's one with gravity. Right. This is the old fudge factor constant that makes everything work. What do they ask me for? Find dFdr. So the first thing is figure out dFdr. R is the distance between the two bodies, the centers of mass of the two bodies, let me say. Right, so if I had a satellite orbiting the Earth, the distance between the two would be the radius of the Earth plus the height of the satellite to the center of mass. You guys kind of with me on the idea of R? So this is just asking, how does the gravitational force change as I change the distance between two bodies? Right? So I don't know if you know this, but if you're in the mountains, if you're surrounded by these mountains, you weigh a little less than normal because the mountain's gravitational pull is pulling you up. Is that kind of nifty? How much, like in the 28th decimal place of your weight, but so this shouldn't be hard. Is that right?
Yeah.
The only true variable is r. I'm not changing what these two things are. That's a constant. So it's just dFdr. Just ignore. And then part B says, then you got to interpret what that means physically. So what do you expect? If I pull two bodies apart, should the force of gravity between them increase or decrease? Decrease. So what should the sign of this be then? Negative. I sort of answered the question there backwards so you can figure out part of the question for part A. Is that decent? Who asked this question? Okay. And then part B is just plugging some stuff in, I think. Yeah. Yeah, part B is plugging some stuff in. Is that, I don't know which part was trouble.
This is just the whole trying to interpret it.
Oh,
Yeah.
So really right here, just interpret this symbol. It's the change in gravitational force as you change the distance between two things. Right? So you can kind of interpret it directly from this symbol because this is what that means. That is what this means. Right? That's why this way of writing the symbol is more useful in terms of interpretation problems. Instead of saying F prime, that kind of hides a lot of shit. Right? This is change in force as you change the distance between the two things. And then to ask you about the minus sign, and now we understand why there's a minus sign. It only makes sense. And then part B really is just plug and chug some stuff. Yeah. Is that decent? Is that okay? Okay. Anything else from homework stuff? Yes.
12B.
In 3-7?
Yeah, on the same 3-7.
Oh yeah. Okay. Were you? No. Somebody came to my office. I can't remember now. Was it? No. So here's a cube. So this is 12B. You almost have to draw this out for yourself. 12B is the one that talks about sodium crystal.
Yeah.
Blah blah blah. It takes the shape of a cube. And then, so it's a cube. So it's x by x by x. I'm just put x is a lot of things. Blah blah. X is everywhere. Blah, blah. All it. First question I have for you is, what's the surface area of this cube?
Is it X?
Well, that's the volume.
Yeah.
What's the surface area? How many surfaces are there? 6. And each has an area of what? So what's the total surface area? 6x squared. I like it. That's a good thing to know going in because it's asking you to show that the cube's volume will change by an amount equal to half its surface area. If you don't know what the surface area is, you're screwed. Right? And that's all it is add up all the surface areas to get the total surface area. It's amazing. Surface area is sort of like perimeter, but in terms of area. how much area to get around something, right? Now here's let me just get started. If I let this cube grow by an amount of delta x, so the length of an edge grows by, I don't know if they make a point of which one. Yeah, okay, cool. We'll use dx. So if I let, like this, every side length is going to grow by dx. Did you get the idea? Now, so I don't want to do it on both sides of this, because then it would have grown by 2dx, and that's not allowed. So this grows by, let me see which way I want to do this. This grows by dx. So these grow by dx, right? Get out of there. Oh, poor people out there. All right, so see how this creates sort of a, that's not bad for me. Can you envision that? There's like a slab on that. So really the question is, and that slab is going to be on 3 of these faces, isn't it? And already I've given away the whole answer there, but you almost need to draw this to explain what's going on. It's sort of the same idea as the tape on the balloon thing, right? So if the radius grows, that means everywhere is going to go out just a little bit. All around the sphere is going to go out just a little bit. Here, if one length grows by dx, it's only going in 1, 2, 3 directions, right? And half of 6 is 3, so I'm going to let you guys get there and figure out what that last thing I said means anyway. Half of 6 is 3, that is ground shaking. If you try the problem out, just remember what I said. There's going to be that slab on top and that slab on the side, right? Whichever side you choose for it to grow out. So it's not going to grow both ways, so not every side gets a slab. Okay. Is that good? Is that decent? I mean, that's really, that's almost done. And you're like, I don't feel like it. I'm going to sit down and think about it. All right, anything else from homework stuff? Okay. So last time we did some stuff that you guys really enjoyed. The related rate stuff, hope to God, I mean, it's just implicit differentiation with some third variable now. So everybody gets a chain rule piece. That's the quick way to describe related rates. Now, there are other little details. If you have too many variables in something, you want to kill something, you want to replace it, right? We did that a few times over yesterday. Okay, maybe. Okay. So today we're going to try to do 310, 311, and get into chapter 4. And I want to have a quiz Thursday. On 3.7 through 3.11. So the last piece of chapter 3.
3.7 to 3.11?
Yep. Okay. So today we're going to do 310, 311, 4142, hopefully. We'll get at least that far. We already sort of did some of 310. I don't know if you remember when we developed a shortcut for square roots. Do you remember doing that? Not really? Okay. Well, let's kind of redo that. So if I have a curve, let's see. Whee. So here is, let's say, A. This is going to be f of A. And I'm curious about, like, I want to know what, I want to estimate what this is, but I want to use, I want to estimate what it is. I want to create a linear function that works well at this point. Now, I warned you about this section coming, and I told you it was just the tangent line. Right? What's the best linear approximation for things that are close to this? The tangent line. Because what's the tangent line do at this point? When you zoom in, we did it up on the overhead. When you zoom in, the tangent line overlaps with the actual curve. It is the straight line that this becomes when you zoom in. So near this point, it's going to do really well at giving you an estimate of the value. And why is it better? Because this curve could be part of this disgusting f of x. F of x could be natural log of the cosine of 1 over x. Oh my God. So that's this ugly looking curve going all over weird shit. And then I got a straight line to use to estimate. And how hard it is to use a straight line. Easy as shit, right? Much better than plugging stuff in the natural log of cosine, blah, blah, blah. All right, how are we doing so far? Is this... So I told you there's a section coming. We're going to make it sound like it's all brand new. And all it is tangent line. And that's the section we're in right now. So how would I find the tangent line at this point? What would I have to figure out to get the tangent line equation? Holy crap. Ooh, Jeff. What do I need for the equation of a line? Yes, because I need the slope, which is the derivative. So f prime at a would be the slope. And I need a point. I've got the point a, f of a. That's the one point I want it for sure to go through. I want to have the slope. I want the line to have a slope equal to the slope at that point. And I want it to go through that point. Right? That's the two things I need for a line. So let me call this, I'm going to call this the same thing they do in the book. I'm going to call it L. This is the linearization. Linearization. Which becomes sort of like, I'm drunk, linearization. This is linearization. It's not me. It's the linearization officer. Can you write the equation of that line for me? And I'll remind you, what's the equation of a line? Y minus y1 equals m times x minus x. That's the equation of a line, right? So you just got to plug shit in. All right, should be done. What's the y piece of the point? F of a. What's the slope? F prime of a. And what's the x piece of the point? A. So I can solve for y. Let me call it L, like I wanted to. The linearization of this curve at the point A is f of a plus f prime of a times x minus a. Let's see why this makes sense. I mean, it should make sense on an algebraic level, for sure. But let's reinterpret this equation at purely calculus level. So right at A, this sucker is going to be perfect. What's the value of the function at A? F of A. And what do you get when you make x A? What do you get here? A minus A. So this piece goes to 0, so you get L is equal to F of A at A. Okay, that's perfect at A. Of course it's perfect at A. We built it around freaking A. It's when I go somewhere that's not A. I go a little bit away from A. Some x point. I want to estimate what f of x is. So what this thing does is it approximates what f of x is for x close to A. Okay, so look at what happens. If I move a little bit away from A, what does the derivative tell me? In fact, doing related rates, it's not just slope. It doesn't tell me slope. I got that. But it tells me if I move a little bit in this direction, it gives me an estimate of how much y should change. So my derivative somewhere is 7 over 3. Well, if I go over 3 units, the output should go up 7, roughly. Because the minute I move away from that point, what might be happening to the slope could be changing. So it doesn't hold over the whole change of 3. The minute I start to move, the slope is changing. That's why it's just an estimate. That's also why I've got to be close to A. Because if I get far away from A, who knows what the function is doing after that? Could be going crazy. How are we doing so far? Everything's kind of trying to tie in together. So what this is kind of cool. At A, it's perfect. This piece is an adjustment piece. It's an estimate of how much. How much do I move times how much Y should change over that motion. That's what this is. That's the adjustment. That's the estimated adjustment to make. So if I go, so that's going to be, here's my guess. That's what L of A would, L of X would be right there. And the actual amount is right there. So there's a little bit of a difference. Now if I go further away, there could be this huge difference. That's why it's got to be close. And that's where the idea of tolerance comes in. So based on what your tolerance is, you can set how far away it's okay to be. Stop. How are we doing so far? So there's a lot of little detail shit, but the bottom line of this section is just find the tangent line and then use it. That's really the bottom line of the section. So, for example, blah, 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 blah. Let's do the same one. So, find the linearization at A equals, what did it say? 1 for f of x equal square root of x plus 3. There's a lot of technical shit. But really, think about it in terms of, you can either think about it just directly in terms of this equation. Just get the parts of that equation figured out. Or just construct the tangent line at that point. They're both the same thing. This is the equation of the tangent line. So you need the slope at that point. Right? You need the point itself. Try to do that. See how far you can make it. We've actually done this before. It's a very similar thing. Catch up to you guys. What are you guys working on here? I would write this as what? Because the first thing you really should be doing, one of the first things you need to do, of course, is to take the derivative. Not just because this equation says you need it, but because we know we need it for the equation of a line. We need the slope. And in calculus, slope is derivative. And you also, so that's the slope. And we also need the point. Yeah, so this isn't too evil, right? What's this guy's derivative?
Root 1/2 times
To the. So what's f prime at A, which is f prime at 1? Be 1/2 times 1 plus 3 to the negative 1/2. So it's 1/2 times, is it very cool what I'm doing? Because I want specifically at the point A equals 1.
Don't you plug in A to the original, not the derivative?
To find the slope, I plug it into the derivative, of course. To find the point, I plug it into the original.
Okay,
Yeah. You make a very soon we're going to be doing first derivative function, first derivative, second derivative, and you're going to want to figure out some stuff. You got to be sure to plug it back in the right one of those three. So it's going to become stupid important pretty soon. Right.
I get confused. So you plug it in into the derivative to find
The slope, because that's what derivative is.
That point.
Good.
And
And to find the point itself, I use the original function like we always have. I like it. So I need the slope, that's dealing with the derivative. And I need the point, well, that's dealing with the function itself. I like it. What it's doing, where it is. So here, this is just 4, square root of 4 is 2, negative flips it, so it's 1/2. Is that decent? Right, negative 1/2 power means 1 over the square root of the thing, the negative power. So I get the slope there is 1/4, that's m. And my f of a is f of 1, of course f of 1 is just 2. I like it. All right, so now we're able to figure out the tangent line, which is also now called the linearization of the function. That's the most sober I've ever sounded saying that word. All right. It says piece this thing together, the linearization of that function at 1. I've got my slope, 1/4. So what's my f of a first off? 2. So it's 2 plus the slope times x minus a, which was 1. So this will be 2 plus 1/4 x minus 4, so it's going to be 1/4 x, 8/4 minus 1/4 is 7/4. Now let me ask you, is the square root function well behaved? You know what I mean by that? Is the square root function a nice, smooth, think about it? What's it look like? In this case, x plus 3, so it's going to start back here. Oh, it's nice. Related to, and that would be a not well-behaved function. Why? Because a very small change in x, and I have a very drastic change in the slope at that point. You see that? So one part of what a misbehaving function would be is that a very small change in x causes a drastic change in the slope at that point. That's one way that it could be. Now, anyway, that's enough right now. Does that kind of sound? So this is a nice, well-behaved, smooth. It doesn't change very quickly. It's nice. So nice. Okay. So why do I say that? Because I want to check this out by using the next good input for x. So what have we just figured out? F of x, which is the square root of x plus 3, is approximately equal to L, which is 1/4 x plus 7/4. Okay. Near what? Near x equal to 1. Because that's what we built it on. That's the place where it works perfectly. So if I go a little bit away from 1, I should be off by a bit. Because I'm using a straight line to approximate a curve. Stop here. So what's an input for x? 1 is good because that's 4. Then I can do the square root. What's a nice input for x that's not far from 1 that gives me a number I can square root? 6 is kind of far from 1 though. I'm thinking about something going the other way. -2. What's -2 plus 3? 1, and I can do the square root, right? So let's check this out. Let's see. Now, do you agree with me though that -2 is kind of relatively far away from 1 in a sense? Yes?
Yeah.
Oh, yes. It could be a very big step, but for a very nice function like this, it really isn't. So let's see. So I'm saying f of -2, which is square root of -2 plus 3, which is square root of 1, which is 1. That's what it really is. Let's see what the linearization would say. So if I just plug in, what do I plug in? -2 for x, right? So what's L at -2? It's 1/4 of -2 plus 7/4, which is -2/4 plus 7/4, which is 5/4, which is 1.25. Not that bad. It's off by 0.25, right? Do you guys get the idea? If I would have chosen x that was closer to 1, then these two would have been much closer to each other. It would have been a much better approximation. Because where does this thing work perfectly? At 1. The further I get away from 1, the more the curve goes away from my straight line estimate. And then I might come back at it, but I don't know, it could do whatever. So a really good question now would be, how do I tell how far away from X I want to be able to go? Well, like I said a minute ago, it depends on how much tolerance you have on the output being off. How off could it be? Does that make sense right there? What did you say? No. So let me see. The visual of what we're doing, A equals 1, and the output would be 2. Scheisse. So let's try and move this. There we go. Boop. How's that? Is that cool? So that's my square root. At 1, the output is 2. So here's the actual line, right? Cool, that's the tangent line we just discovered. Are you with me? It's got a slope of 1/4, right? Where'd it go? Over there somewhere, 1/4. Here we go. You guys with us? That's the visual of what we just did using calculus. Okay. So we just tried an input of -2, and we were off by 0.25, that little bit right there. Do you see? We're off by that little bit. So what we want to say then is, let's say we want to be off from the real value by what? What sounds like a good tolerance? I don't want to be off by like 5. That's a lot. In fact, do you guys agree that 0.25 is still kind of a lot to be off by? Yeah, in some situations, that's like, forget about it. No, people get die. Right? You want your tolerance to be. Let's say we want a tolerance. We want to be off by. Oh, how do you spell tolerance? That's a good job, Jim. Tolerance. That looks more like Toblerone. I don't know. We want to be off by, let's say 0.1. How's that sound? It's a good place to start. Okay, I like it. So let's see. How do we do that then? I want what this guy says to be 1 off from what this guy would say, right? Do you understand what I'm saying? So if I go too far, do you see if I go and see this difference there? That looks like it's almost a difference of 1. That's too far. Here's my place where it works perfectly. The minute I go either direction, it's going to be off. There's going to be a difference between the purple line and the actual black curve. So I'm trying to control that difference. I want to control that. I want to say if I want, let me try to write it down for you. Let's summarize what we got. So for f of x equal the square root of x plus 3, the linearization is 1/4 x plus 7/4. And of course, if you check it real quick, plug a 1 in, what do you get? 1/4 plus 7/4 is 8/4, which is 2, which is the exact same value you get there. That's how we built it, so that's not a surprise. It works perfectly for the point we built it around. I like it, because that's where the tangent line touches the curve. So of course it's going to be the same. I want the output for this guy to be at most 0.1 off from this guy. Does that make sense? All right. So how would I capture that mathematically? Like how would I set up? There's an inequality hiding in there somewhere.
Less than.
So I want the. So what's the actual output to this? It's square root of x plus 3. That's the actual output to this, right? So I want the output to this to be captured between that and that. I think they do oh wait a minute. Oh, okay, so they do eventually do that. This is like an example 2, okay. So this one I have to do on the graphic calculator. Let's do that right now. I didn't bring any, so you can just watch. You might see something like this in the homework. But you see how this is exactly what we just said? I want him to be at most 0.1 more than this, and at least 0.1, less than this, right? That's at most 0.1 less, right? I don't want it to be more off by that. Okay. Let's use the computer one. There we go. Sweet. It's waiting for me. Okay, so if I put in here these three things, if I put in here square root of x plus 3, minus 0.1, and then I put in there 1/4 x plus 7/4, and then I put the square root of x plus 3 plus 0.1. Let's say, what was it? Yeah, zoom 6 just to make sure the window's nice. There's the minus 0.1. There's the linearization. Oh yeah, it's all happening. It's within 0.1. So what's the most important kind of point up there? What's the most important point of this whole thing? You can do it. You can do it. What's the thing that got this thing going? What point? 1. A equals 1. All right. So if I can zoom in, one of my favorite things is a little zoom box. I want to zoom in and all the shit happening around x equal to 1. So here's x equal to 1. Let me make a box. Starting in here and move it and really zoom in around 1 here. Okay, that's probably good. All right, there's the lower thing. I think I put that in first. There's the linearization, and there's the upper thing. All right, so I went a little too close. What I'm looking for is where these things cross. That's going to determine where I go down to and up to. So if I zoom out a little bit, let me make my window. Oh, what's the best way to do this, Jeff? Yeah, I want to go, let's go from -1 to 3. See, I'm just increasing how much I look left and right, because it looks like it's going to meet out there somewhere. All right. There's the floor. There's the thing. I think it meets the other dude in a couple places. Yeah, meets down there and up there. I just want to go a little further out. Oh my God. 1.5 to 3.5. Now we should be able to see this. There's the floor. There's the straight line. There's the ceiling. So that's where it crosses there. And it crosses there. So now I just got to find those two intersections. I think we did that one a problem like that before, right? If I find this intersection, how do I do that? Did we do that in here yet? Yeah, second calc number 5 intersect. Let me show you people at home what we're doing. So now it's going to ask me, what's the first curve? I want what two curves intersect are the line and this guy. So let me go up. There we go. Here's one of the curves. The line is another curve. And now I want to get close to the intersection. Woo! The intersection's down here somewhere. In here somewhere. That should be good enough. There we go. So they intersect at -1.13, let's say. All right? So -1.13. And then the top one, I do this again, intersect. Just pull it over here so we can see what I'm doing here. There's the line. You just go straight to the answer. Top. The line, the top dude, I want the intersection of those guys. And there's my guess. Oh, and way down there, I love that shit. It must be off the screen still. Damn it. So, but I just do that same thing to find where they meet first. And I guess this one is still off the screen. I have to look further up. But I find that intersection also. It looks like it would probably be... Oh, you guys are all like, what the shit? I want to see that intersection. Okay, that's where it is right there. Let me just give an estimate. I'm not going to go through all this. It looks like it meets around 3.7 something. So let's say this is 3.7. So if I want to be within 0.1 of the answer, and I really, just to kind of really overdo what this is doing. So if I see, when is my approximation in between? When is my approximation in between these two things? When it hits that and when it hits that. In between there, it's in between those two. You see what I'm saying? The minute it's past this, now my approximation is bigger than what I wanted to allow. It's off by more than what I wanted to allow. That's why this is the way to do this. So when we used -2, we were off by 0.25. -2 is well below this. That's where we were more than 0.1 off. If we would have used -1 or something in here, we would have been less than 0.1 off. Okay. So that's the idea. There's error tolerance in there that tells you how far. The whole idea of close is really weird in all different levels of mathematics, but here's a place where we have to have an idea of what's allowable error, and then I can figure out what's acceptably close. Of course, if this is too big of an error, somebody else is like 0.01, then I'm going to have to be a whole hell of a lot closer. This would be a whole lot narrower, right? That's another good drunk word, narrower. Does that make sense? If I made this 0.25, this would be bigger. It would have -2 in it, because I know at -2, we were 0.25 off. Okay. That's the only weird extra shit on top of just finding a tangent line. That's what the linearization is. But they have this extra little layer of what is close enough. Well, that depends on how acceptable, how off you could be from the actual output and still think it's okay. That's the idea of the tolerance, how tolerant you are of differences. That sounds more like Starbucks training. But one afternoon, and it's all solved. I love it. Let's see. I think that's all there is in here. There's one extra little thing in 310. I better turn it around. This idea is going to come back a few times. This is the first place we're sort of really working with it directly. It's the idea of differentials. So, if y is f of x, here's what the differential is. Now, normally we would say like dy dx is f prime of x. Is right? Is that cool? But it's almost like a definition of the notation. But here I can say y changes by an amount equal to the slope at the point times how much x changes. I can multiply dx up. Now really, so y would change by an amount equal to the slope at a point times how much the x changes from that point, which is really what we just did. I want you to realize this. What we just did was we said that, where's f of x minus f of a, which is how much y changes, is equal to f prime of a times how much x changes. Right? Isn't that the formula we just used to figure out L? Yes?
I wonder if could you apply that to tolerance as well? Set the tolerance to the change in y?
Especially when I bring in, let me bring in different notation. It's going to be more used to what we're, because these symbols supposed to mean infinitesimal change. Like how big of a step? Well, whatever you think, cut that in half, and keep cutting it in half until you go crazy. So dy is like, dx is like a stupid small change. So I want to make a bigger change. So would you say that 0.0000001 is a very big change? No, but it is related to this. It's infinitely bigger than what these represent. These represent point, infinite zeros, and then a 1 of a change. So let's bring in bigger steps, more like what we're used to, right? So delta y, right? Let me write it the same way they got it. Yeah. This is what we use now. Now tell me how this looks similar to what we've done in the past. What does this look like? What does this look like? The limit definition of derivative, the top of it, right? Because this is how much the y's change. If I make x change by delta x, then how much will the y change by this much? So really all it's saying is, here's x, here's f of x, right? So if I go to x plus delta x, how much will the y's change? Well, by the difference in the outputs, right? That's all that's saying. But this is a big step. This allows for bigger steps. That symbol right there is the big step related to this infinitesimal thing. This is called a crude change. Like a change of 0.01 would be this. So you got these two different kind of ideas. This is